Hello, everyone. Thank you for joining this Wednesday seminar. I'll be introducing our seminar speaker, Professor Robert Hyers. It's an honor to do so. Hyers had his bachelor's in material science from MIT and his PhD materials engineering also from MIT. And he proceeded to NASA to work there as a staff scientist for 4 years. I'm working on the electrostatics levitation, working the levitation lab. And then he also was an executive director of the University of Massachusetts. And he's currently the president and chief technology officer, or he worked as the president and chief technology officer in Boston Electrometeorological Corporation, currently known as Boston Metal. And currently he's the department head Engineering Gustav Polytechnic Institute. He's also a professor in University of Massachusetts, and he's a principal scientist and the owner of RAA Materials LLC, which is a company that provides and contract research on high temperature materials processing for clients in the aerospace and extractive industries. He has two projects. Currently has two projects. The first that is in the additive manufacturing of by cold spray, and also 3 different NASA flight projects on the International Space Station. So today he'll be giving us a seminar talk on getting the most from models in high temperature materials processing. And with that, I'll welcome our seminar speaker to go ahead and stop sharing.
Okay, thank you. I need to switch the HDMI input for the projectors. There, good. And now I need to find the Zoom window and share this window. Okay, share, display 2, go. Okay, good, thank you. So thank you everyone, thank you for having me back. I look forward to joining the faculty here in January. And until then, I'm happy to be the visiting seminar speaker one more time. So I was specifically asked to give an encore presentation of the talk from 2019. So maybe a few of you have seen it then, and I hope that all of you will find a little something new. So let's see, come on. So today I wanted to start with a little bit of philosophy of modeling. What to model, how, and why, and where does modeling fit in the grand scheme of investigation and discovery. And then I brought a few examples of some applications that are from our research that may be of interest to you, and a little bit from industrial application, and then a little bit for you grad students about how people pick projects and how you might want to think about which projects to work on when it's up to you. And for the faculty colleagues, many of you have seen many of these slides before. There are a few new ones, and I hope that you'll bring some questions that will make it worth your trouble to have come here. So let me start with the assertion that models link theory to experiment. And so the theories are, what do you think is happening? And so in terms of Isaac Newton's discovery, well, when he got hit by an apple, he thought masses attract. And the model is, if these theories hold, what will you observe? Well, first you'll observe that apples fall down. And second, you'll observe they fall with a constant acceleration, so the velocity increases with time. And then as you get more and more sophisticated models, you get larger effects. What happens if you drop an apple for hundreds of meters? Well, it reaches a steady state velocity. And if you drop an apple for hundreds of thousands of kilometers, then you find the acceleration is not constant, but depends on the distance to the center of the Earth, and so on. And then you come back to the connection to the experiments. Is the observation consistent with the prediction? And for this, you need the model. And then always, what else did you observe that may not have been part of your original specification? So the theories are sometimes very specific and sometimes very general, sometimes just practical. That we think these things will react, or we think that corrosion will not be a problem in this situation. Sometimes they're very specific. We think that the time dependence will have this functional form that's connected to the differential equations. It all depends on what you're investigating, how mature the knowledge is, and from this you can reinforce the design of the experiment. What do we need to measure and to what precision? And all of this is connected through the model. So if the theories hold, what will you observe? And often you'll discover data that are missing, that you can't learn what you wanted to learn from the experiment you thought, because you need more input from thermodynamics or transport. But then also there are some things that some places you can use the model to measure things that are not directly observable. So you measure temperature versus time, but through your model, you can determine the energy of reaction. Or you'll see some examples later where we back out constants in the constitutive relation for properties through a model by observing something different, in this case, displacement versus time. Another essential part are what I call scoping calculations. These are sometimes, usually, but not always very short, but trying to say which physics are important. So back to the Apple example, if you want to decide whether or not air resistance matters, well, you have a model for aerodynamic drag on spheres. And an apple's not a sphere, but it's close enough to decide whether or not aerodynamic drag is important. And it turns out that apple trees aren't tall enough for aerodynamic drag to matter. And so in half a page, you can decide you don't have to include anything to do with drag, much less direct simulation of turbulence in the wake. And so these are the kinds of things that we use scoping calculations for, is to focus our efforts appropriately. And so I talk about this in sort of a Mythbusters framework, that you have a hypothesis, aerodynamic drag matters, and your result is confirmed, plausible, or busted. And in this case, if you're dropping an apple from an airplane, aerodynamic drag is confirmed. From an apple tree, busted. So the experiments come back to, is the observation consistent with the prediction? So did you get the conditions that you specified? Is everything okay? All right. So you want me to... Here, I'll let you drive. Click here and mute there. Okay, good. So then also, an awful lot of serendipity comes from trying to measure X and discovering Y. There's a story I tell in class. People were doing experiments on tetrafluoroethylene, and one of the tanks came out empty. They weighed it and it had the right weight. So the supplier said, you know, I don't know what you did, but we put our gas in and see it's the right weight. When they cut the tank open, they found this pasty white grease in it. This was the discovery of Teflon, polytetrafluoroethylene, and some impurity in the lubricant that shouldn't have been in the valve initiated the polymerization, and all the gas turned to grease. And so now we have Teflon. You're always looking out for things like this, things that can't be in your model because you didn't know that you should be looking for them, but you need to be aware. And when that happens, then often you will apply a different model to connect back what you found in your experiment to the original theory and to a new set. Also, sometimes you'll use this model here to assess parameters that you can't measure directly. You'll see an example later where we want to measure the fluid flow in liquid metals that are suspended by electromagnetic fields. And you can't measure that directly, but you can use a model to get the whole flow field distribution from the parameters that you control. And we use that for lots of different kinds of research. So here's the question that always comes up. You have a model and experiment and they disagree. And the question is, who's right? Well, modelers always believe the experimentalist, and the experimentalists split about 50-50 between, of course I'm right, and, well, CFD magic. But really it comes down to, what was the question again? So if your assignment is simulate this experiment, then the experiment is right by definition, but the information passed to the model often will be deficient in some way, that the boundary conditions you got in the experiment are not the ones that you specified in the model. But also often, both the model and the experiment are charged with achieving certain conditions. And then in the model, you can be pretty sure that what you put in is what you got out. But more modeling and different modeling can help you verify that the experimental conditions you achieved are the ones that you had specified. And this is the first example. So I'm going to be talking about radiators for nuclear electric spacecraft. So a typical spacecraft would have a radioisotope thermal generator that makes about 100 watts, and that powers everything. But if you allow fission power, then you're looking at hundreds of kilowatts or more. And this is great. It enables things like electric propulsion that is incredibly efficient and lets you get planetary transit times in weeks or months instead of years. The problem is that you have to reject a lot of thermal energy to make 100 kilowatts electric. And so here's a reference architecture for the Jupiter Icy Moons Orbiter. And let's see if you can see my cursor here. No. Try this. Okay, well, all the way at the tip of the point, about 1 pixel on your screen is the nuclear reactor. And then behind that, you have a big cone of heavy metals for radiation shielding to protect the ship from the radiation. And then the big triangular thing is an array of radiators for rejecting heat to space. On the ground, you build a nuclear reactor next to a river for the cold side of your thermodynamic cycle, but there are no rivers in space. So you end up with this radiator that's about the size of a football field for this little spacecraft. And that radiator is about 40% of the ship mass. And you compare that to a payload of about 5%. So if you can change the mass of the radiator even a little bit, it has an enormous impact on the mission capability. So we looked at applying high thermal conductivity materials. And so you hear a lot about graphene, very high thermal conductivity, but it comes in sheets that are only 1 molecule thick. And a big graphene domain might be, I think, a few microns. There may be some that are 100 microns at research scale. The next level is carbon nanotubes that still are very exciting, but they have the same issue as well. A very big carbon nanotube multi-walled might be hundreds of microns long and a few tens or hundreds of nanometers in diameter. And all of these interfaces between the parts scatter phonons, and so they reduce the thermal conductivity of a big part. So we have available some high thermal conductivity graphite or carbon fibers that are here up to about 1500, about half the thermal conductivity of the carbon nanotubes. And these are macroscopic. So the structure looks kind of like the cartoon. So if you imagine rolling up graphene like a newspaper, then you understand the structure of these high conductivity carbon fibers. And by the processing, they make the domains quite large so that you get this high thermal conductivity. And I see a bunch of questions in chat. Let's see. And they're all about the echo. I'm glad it's resolved. Thank you. And I have control on this computer. So our approach was to incorporate these high thermal conductivity fibers. And one of the competing technologies for this temperature range is carbon-carbon radiator, composite radiators. These have a couple of problems. They're a lot heavier than our design because the carbon matrix contributes very little to the conduction of heat, contributes a lot to mass. It also contributes a lot to structural strength, but in a place you want not to have it. That the carbon-carbon radiators fail by delamination of the braze joint between the carbon-carbon and a metal heat pipe. And by going to 10 micron fibers, we prevent that delamination. If you want to think about it in fracture mechanics terms, the stress intensity goes as the square root of the crack length. And so if you have a part that's 10 centimeters wide in little bitty panels, then your crack length can be 5 centimeters. Your stress intensity is really big. If you have a 10 micron fiber, then your crack length is limited to 5 microns or so. And so your stress intensity is about 100 times smaller, so it doesn't crack. You get elastic or even plastic deformation in the brace to accommodate the thermal expansion mismatch. So the net result of all of this is that our panels are about 60% lighter than carbon-carbon, according to the model. And so we built a machine to test. And so you see bright yellow-white in this infrared image is the heat pipe. And then the kind of raggedy red and purple things are the carbon fibers hanging off. The braze joint is just along the left edge here. And it looks like victory. The blue line for the model goes right through the red line for the experiment, but only with one adjustable parameter, the effective thickness. And that turns out to be wrong. It's qualitatively correct, but the thickness doesn't match by more than a factor of 2. So who's right? And we went through the model, compared analytical results. Our model was working, our software was working, everything looked great. We took a closer look at the experiment, and it turns out that that big bright tube has a significant view factor onto the fins. So we're heating the fins by radiation from the heat pipe directly, as well as by conduction. So when you add these copper heat shields, or radiation shields, so that you have only conduction through the fins, then the situation gets better. And here we've got the fit of the new experiment against the original model with no adjustable parameters. And it goes right through the middle. So in the course of this project, we also made an interesting discovery. We looked into what happens with the emission of radiation light photons from this kind of furry array of fibers. And it turns out you get an enhancement in the emissivity that's about half the distance to the goal line. So if you look at the red curve, the dashed line at 0.6 is what you'd get from a flat fin with an emissivity 0.6. And if you have an array of fibers, then depending on the fiber volume fraction, you can get up to almost 0.8 for the emissivity, almost half the distance to 1. And this is a property of the multiple scattering from the depths of this furry array of fibers. So where is this? We had some follow-on grants from NASA and from NASA Marshall. Something I just encountered this summer is they cited our papers in a call for proposals from NASA Early Stage Innovations. They had written me the nicest rejection letter I ever got that said, basically, you've outgrown us, find someone else. And we've gotten inquiries from the Jet Propulsion Lab and satellite manufacturers. And then also, of course, I want to show you this. On NASA's fellowship site, they have a picture of my student, Dr. Brianna Tambulian Brown, working in her lab at Marshall. And they still use her picture about our radiators. So next I want to talk about something else. I'm not sure I like this language, but I have to accept it, an inverse model. The idea is instead of trying to use, so forward model, you use known parameters to calculate an unknown result. An inverse model, you use a known result and calculate the unknown parameters. So what were the boundary conditions that give this result? And so sometimes you can directly invert the model, but for something complicated and nonlinear, that often doesn't work. So you use iterative methods. And the one I'm going to show you is non-contact measurement of creep. So I think everyone here has a good idea of what creep is, that under constant load at high temperature, materials deform. And creep matters for all sorts of high temperature applications. And what is high temperature varies, of course, depending on what you're doing. So anyone who's played with silly putty knows that it creeps at room temperature. If you make a ball of silly putty and leave it on the desk overnight, then you come back to a puddle of silly putty, and that is creep. So conventional creep testing looks like tensile testing. You apply a constant load and let the sample sit. When I was applying to graduate school, I got the advice, never work on a project on creep, that your first day you'll load your 1 year sample into the creep frame. And when that finishes, you graduate. But the power will go out in 3 months, in which case you have a low stress 3-month sample and you start again. And so I did not do that, but one of my students did. We contracted out some conventional creep measurements and they look just like what you're used to. And these are typical results for pretty good measurements. These were done in a national laboratory in Japan. And you see that you get a nice fit. The points correlate nicely to a line that fits the functional form for this power law creep. And you see the scatter that gives you an uncertainty in the stress exponent of plus or minus 1. So this is not an uncertainty in the creep rate of a few percent. This is an uncertainty in the exponent. So the variation is huge. What we did was to take a 2 millimeter sphere and spin it. It turns out if you spin it at 30,000 revolutions per second, 2 million RPM, you get 100 megapascals shear in the center. And then you can heat it up and watch it deform. And you see that creep occurs here. So in this case, we were accelerating the sample very slowly by photon pressure. This is a pure niobium sample at 1985 degrees C, the same temperature and material as the previous plot. And after about 5 hours, the deformation becomes noticeable. And after about 7 hours, you get the end result there on the bottom. Interpretation, however, is a little trickier. So we used a finite element model to run different combinations of parameters to the same equatorial strain. And you see that for the same equatorial strain, you get different polar strains, very slightly different polar strains, depending on the stress exponent in the equation. And so we already had a precision metrology system in place that let us measure the small displacements of the sphere with an accuracy in the range of 100 parts per million. And so this displacement of 0.02 millimeters is very well within the capabilities of the system. And so once we run the model, we just match up the experimental result here, 1.767, corresponds to a stress exponent of 2.517. And yes, all 4 figures are significant. And, or sorry, the first 3 are significant. So our test, the stress exponent 2.52 plus or minus 0.02. Our conventional test 2.4 plus or minus 1. We looked at a previous result, which strangely enough also used a rotating sphere, and they got 2.5 also, but didn't do an error analysis. And the last one is kind of interesting. We looked in the creep mechanisms map book compiled by Frost and Ashby, and it says 4.4. So what's going on there? Well, we found the original source paper that they'd cited, and those results were extrapolated from measurements at 1200 C. And so the conclusion is that you have to know all the mechanisms to know whether or not you can extrapolate the measurements. In this case, a design based on extrapolated measurements would work, but it would be too heavy. So for our inverse model, we measure the deformed surface shape. We iterate a finite element model to match the deformed shape. In this case, I wrote a little control loop to use a numerical method to adjust the parameters, all under control of a Perl script. And we read out the results. So there's follow-on work for NASA. We did a project with niobium silicide superalloys for GE. We did screening for the J2X engine that is the upper stage for the new NASA rocket that's supposed to launch any day now. And the project continues with refractory alloys from my student who worked on this, who is now faculty at Iowa State. So virtual sensors. This is the next topic. The idea is to use the model to predict parameters that are hard to measure directly. So for our fluid flow in liquid metal droplets, it's driven by either Marangoni convection or magnetohydrodynamic flow. And we have different reasons for different experiments that we need to quantify different things about the flow. So there are a lot of experiments that set the droplets oscillating to measure properties like viscosity and surface tension. There are other experiments where we showed that mechanical drag from the fluid flow can affect the phase selection, the nucleation of a second phase during solidification. And then the last one that I'm going to show you one slide on, or two slides on today, is how the fluid flow affects the concentration field around growing nuclei. So in this system, we have an opaque featureless sample, so you can't use a lot of the methods you'd like, no laser Doppler velocimetry or particle tracking. The sample is high temperature and highly reactive, so you can't put a magnet in it to use a Vivis probe. And if you do have a composition where you can put particles on the surface, and we do sometimes, those get swept into the stagnation line, so they don't tell you much about the fluid flow anyway. So the fluid dynamics is governed by the Navier-Stokes equations, and there's some details here. And we're applying this for electromagnetic levitation. So we use a coil to induce currents in the field. The imposed field, or the induced field, opposes the applied field, so the sample tries to run away. And by controlling the shape and magnitude of the field, we can make the sample run away just enough that it floats here in space where you don't touch it. And so having done that, you have the opportunity to provide an environment that's free of heterogeneous nucleation, at least to a large extent, and to do other things to the drop. So here is some colorful fluid dynamics about the flow in these levitated drops. These drops are symmetrical, which is characteristic of drops in zero gravity. And in this case on the right, we've plotted the shear rate. So it turns out that the shear rate in the flow determines the extent. And so this information can be combined with results from time to solidify to get plots like this. So the left axis is the pre-exponential factor in the nucleation equation, and the right or the bottom axis shear rate, that's ours. And this appeared in a paper in Nature Microgravity. And then again, here's my former PhD student, Gwen Bracker, showing her Scouts BSA for Girls troop as she's running experiments on the space station from the control station at the DLR in Cologne, Germany. And she's now a postdoc there. So where is this? Experiments continue on the International Space Station. We were supposed to have time next week, and it's been postponed for a month. So probably in October, if other things go well with everything else on the space station, then we'll all be there running nights from Cologne. And there are literally dozens of experiments that we have some supporting role in providing flow calculations for. So one more part, I wanted to show you a little bit about how this is not all just flying 1 gram samples in space, but also has some ground-based application. And so this is a company that I had the opportunity to work with for 3 years on a 1-year leave. And I'll show you a little bit more about them in a minute. In this picture, you can see the silhouette of a worker wearing one of those silver suits. Her uniform is dark in this infrared image because the silver suit is reflective and insulating. But it also gives you an idea of the scale of the machine. And I'm pretty sure that that's K. I'm not 100%. It's hard to tell. People in silver suits look pretty much alike. So the application was molten oxide electrolysis for iron. We were looking to scale up a process developed by Don Sadoway at MIT. So first, why bother? Well, steelmaking is over 8% of all anthropogenic CO2 and almost 5% of all human energy usage. And their calculations showed you can cut the energy usage by 1/3. With the current power mix in the US, you can cut the CO2 by 1/4. And when the renewable energy guys do their job, it'll drive the CO2 to 0. And oh yeah, steel is a $1 trillion annual market. So there are a lot of opportunities for niche products to get a foothold and to grow over time. So in principle, it works just like electrolysis of water, that you pass a current, and if you do everything right, then you get, in this case, steel on the bottom and oxygen gas on the top. And there are a lot of details to make this right, including details that are different from the lab cell or lab scale cell for those that are not tripping over their tongue. So this is about the size of a coffee cup. And this was this was presented in 2015. And this is what a lab cell looks like. And you pass current and you get metal that drips off the bottom of the anode, or you get metal that drips off the bottom of the cathode, and the anode makes oxygen that bubbles up, and you can see the bubbles. Now, to scale up from that coffee cup size thing to this reactor that they published an article about in Advanced Materials and Processes, you had to increase the current 1,000 times. So it goes from coffee cup size to a little bigger than the table here. You have to go to internal heating versus external so that all of the necessary heat to sustain the process is provided by internal resistance in the system. It has to be designed for a lifetime of years versus a few hours. And you have to be able to feed new ore and tap out the product and so on. And you can imagine there's a bit of modeling involved in making this work. So we used to talk about how the aluminum industry was then 105 or 110 years in, and we had to do it in 2. So again, modeling is going to matter. So I'm not going to talk about any modeling that might or might not have occurred for that company for reasons you can imagine, but instead I'm going to talk about very briefly a generic problem in lots of metallurgical processing operations, which is containment of molten metal and molten oxide at the same time. There are lots of ways to contain a molten metal. Crucibles, there are maybe a dozen different materials that are common. There are lots of ways to contain molten oxides, usually in a metal, but the liquid metals attack the solid metals and the liquid oxides attack most of the solid oxides. And so to get it all at once is pretty tricky. And so one common way is to have a frozen ledge of electrolyte. This is used with the fluorides in the aluminum cells. And so you wanted to maintain a frozen ledge that's the desired thickness and morphology, so that it contains the electrolyte where it's in thermal equilibrium, and the metal where the frozen ledge is so different chemically that they have limited interaction. And you want to do all of this while minimizing the energy cost and maintaining robust equilibrium, so that when you have an excursion in the cell, you don't lose the ledge, because usually then you lose the furnace. And what happens then depends. On the research scale, well, you make a mess, you clean it up, you go back to work. On the production scale, probably people get killed. And so you want to make really sure that the inside stays inside. And so this is a really complicated electrothermochemical fluid problem that is cross-coupled with lots of different phenomena that all matter. And then, oh yeah, if you're doing this, you want to apply what you've learned to a wide variety of other products over a huge range of temperatures and chemistry. And so again, models are the way to get that rapid application of what you've learned. So an approach for dealing with these really complicated phenomena: first, you start with scoping calculations. You decide what matters for me today. And so you go from a list of maybe 100 things you might want to put in to the 5 that have to be in for the answer to mean anything. And you do this through sensitivity and uncertainty analyses. The scoping calculations also tell you about one-way versus two-way coupling. So in our magnetohydrodynamic calculations for the levitated drops, you can look at a single dimensionless group, the magnetic Reynolds number, that tells you the magnetic field drives the flow, but the flow is too slow to change the magnetic field. So that's a one-way coupling, and you're done. You don't build the reverse coupling. And then you have to dig up properties and their uncertainties. So of course, first you start with literature, and then you have to do some measurements. There are lots of correlations that you can use that are sometimes accurate enough. Sometimes you have first principles models or DFT or molecular dynamics simulations, and these are getting better and becoming more useful every year. And in the end, you figure you have a bunch of properties and some uncertainty measurements, and then you have to do something with them. So I wanted to show you an example of how you can apply simple correlations to tell you about the relative importance of these uncertainties. So here you've got a correlation for forced convection that came out of a standard textbook in heat transfer. The Nusselt number is this function of Reynolds and Prandtl numbers. And so when you expand this in terms of properties, the property that will spill your lining is the heat transfer coefficient. That's the one you have to control in the design phase, and it has these dependencies on the different properties. So we look at a few of them. Proportional to the 2/3 power of thermal conductivity. That says you need to spend a moderate effort to get that right. That 10% uncertainty in thermal conductivity will cost you 6% in the heat transfer coefficient. And you're probably designing so that nothing terrible happens with 100% error in heat transfer coefficient. With viscosity, the dependence is smaller, which is good, because it's really hard to get viscosity that's repeatable better than about 25%. When they do round robin studies, sending samples of the same heat of metal or of slag to different laboratories, typically 25 to 50% variation is what they measure, and so on. So here, with 20 minutes work, you can decide how important these different inputs are and which things should you spend $100 or $100,000 measuring more precisely, and which things can you say, well, metals have a conductivity of about 100 watts per meter K, done. Oops. And so now you can build the models. So you might want to build an electrothermal model and find an element, do some CFD, do some CalFAD simulations to look at your system and what's going to be in your ledge and in your electrolyte, and so on. And then you build the models, and it's not just one. That some people build their whole careers on the grand unified model that has everything in it. And there are problems where that's appropriate, but there are an awful lot of problems where that's at least not where you start. And the idea is to iterate designs fast, that a full-scale model with direct simulation of turbulence in an aluminum reactor might run for a month on a national supercomputer. And one of our CFD models in the drop with the proper dimensionality and just the relevant physics runs in about 1.5 minutes. So we might run 100 in a day. And remember always what you're there for, to answer the questions and solve the problems. So where are they at? Well, in 2019, they published this article announcing their first venture capital funding, $20 million. And just a month ago, Boston Globe did a nice feature on them where they said that the company's now raised $85 million. You also see in the picture from a different popular media outlet, there's again a person in a silver suit standing next to a cell, and this one's a whole lot bigger and squarer. So they've announced that they'll be doing commercial production over the range 2023 to 2026. And then we'll find out whether the economics really work and whether this can really make a dent in the global CO2 production. I'm hopeful. So to wrap up the technical part of the talk, it's a cycle. Model connects theory to experiment and experiment to theory. And by keeping in mind always what your objective is, you'll design different models for all the different phases and be able to get to what you're looking for. Then the last part, I've got just two more slides because Adam asked for them once after he saw them before. I thought they might be interesting to you. So how do you pick problems? So to me, I think most of the interesting problems are at the boundaries, and mine are between the physical and virtual world, but also between disciplines, fundamental applied, or a new application. And if you dig down one level, here are the ways that I've picked projects. So on the left, there are different categories. You have inspiration. I have an idea. I wonder if a bottle brush is a better radiator than a flat plate. It turns out it isn't, but in the course of investigating that, I figured out that you don't need the matrix, that the rest of the radiator works at least as well. It turns out it works better if you can leave that part home. The non-contact creep method came this way too, that Peter Liao from University of Tennessee asked, how can we apply a mechanical load to these non-contact samples? And so I had an idea. And now it goes, if you want to measure creep at 3000 degrees C, what do you make the grips out of? So we use inertia. Invitation, these are my favorite kind, but they're also the hardest to get. We have a problem, can you help? And so when one of these comes by, be sure that you can help and then say yes. And so, you know, I've been around a while. I get these questions, and maybe a third or a quarter of the time, yes, I can help you. And maybe half the rest, it's like, go talk to my buddy down the hall. And the rest, it's like, wow, that's an interesting problem. Then there are collaborations. People say, you know, we had fun last time. Let's do something new. What can we do together? And so the only constraint on the design space is that we can all do this together. And this happens. It's great when it happens, when it works. And I've gotten the opportunity to be in some of these. There are targeted growth areas. I want to play in this thing because it's going to be big. Sometimes it's really hard to get traction. Sometimes you don't, but sometimes you do. And the last is, I want to solve the problems that matter. And this is a very difficult starting point. It is a feature that you can use to choose among opportunities and the others. But if you say, I want to fix energy, but don't have an inspiration and aren't invited to join a team, then it gets pretty hard to get that first step. So anyway, I hope that these will help you think about where the projects you're working on came from, and that when you are a little further along, that they'll help you think about where to spend your effort on learning about the landscape in different areas, on building teams, and on whether to say yes. So thank you very much. Okay. Good. So I'm happy to take questions. I will try to adjust this screen so I can see the chat. Okay. Yeah. Professor Brown. Uh-huh. Yeah. So this says find ground that take the path less traveled by. Yes. Good. Road less traveled by. Yes. Good. Thank you. So other questions? Yeah. Professor Powell. Okay, so for those on Zoom that probably can't hear, his question was, texturing is often used to increase emissivity, and how does that relate to the effect that we described in the paper about multiple emission from cylinders? So if you have the cylinders touch, then it reduces exactly to texturing of parallel grooves. And it turns out that texturing is usually not reentrant. So you very rarely have multiple scattering from textured surfaces. Sort of the limit is the standard black body, which is a small hole with a big cavity behind it. And if you had used pitting corrosion for your texturing so that you end up with a structure like that, then you can accomplish emissivity approaching 1. Emissivity exactly 1 in the holes, and then emissivity whatever it is in the material between the holes. So does that answer your question? Okay, good, thanks. So that paper came out of a class project, actually. Bree needed a 800 level, PhD level graduate class in radiation. And so we published an ad, and sure enough, got a couple other people so she'd have someone to study with. And their term project was pick a difficult problem in radiation and do something about it using the methods in Siegel and Howell. And so she wrote a Monte Carlo ray tracing code to look at scattering from cylinders. Another guy who is now faculty somewhere was looking at flash heating of powders for synthesis of chemicals from biomaterials. And so he did something different, and so on. So that was pretty cool too, that their term papers ended up as journal papers. Yeah, Professor Maradi. Okay, question, who did I work with at Marshall Space Flight Center? So I had been on the staff there before I came to UMass. And so I started working with my friends, and then the network grew as we had something to talk to other people about. So it was Jan Rogers at first, and then Mike Sansushi, who had actually been my master's student and is now my PhD student from there full time after he joined. And then the next circle was the thermal design group from NASA Glenn. So come on. So anyway, they had a group focused on radiators. And I'm blanking on the name. Of course, I should know, but it's been a few years since I thought of it. Lee something M. Yeah. Okay. Question. Do I know what's wrong with the current heavy lift sitting on the launch pad? That's an easy one. No. Okay. So people at another meeting were talking about it. I have no idea how well informed they were, but they are propulsion types from NASA and from the private space companies. And they're like, yep, it leaked. We told you it would leak. When they fix the leak, then it'll work for a little while, but they really should have done it our way. So I don't know how well informed those opinions are or not, but people who have expertise in one area have identified that their area is, of course, the source of the problem. Okay. Yeah, thank you. So the question was about virtual sensors. I adopted the terminology from the dynamic systems and controls community, but the principle is the same. And the part that excites me about this is that the details are always different. It depends on what you want to measure and what you can measure, what goes in between. And sometimes that's a reduced order model that looks like an algebraic or differential equation. Sometimes it's a full up CFD simulation. Sometimes it's just a table. It depends on what you're solving. Thank you. Yeah. Okay. So the question was about the ratio between experiments and models at Boston Metal. And other than it was everything all the time, so tightly integrated, you couldn't see the boundaries. I won't give any more details. That they appointed a modeling guy as chief technology officer and charged me to see the experiments succeed on a very aggressive timescale. And so we were all doing everything we could with discussions, often multiple times a day, about different possibilities on both sides. And it was fully integrated. So we certainly did not have, and we would not have succeeded if we had had a modeling department and an experiment department. Good. So, anything else? Thank you very much, everyone. Okay. Good. Thanks for coming.